So we're going to have a session now on looking for different ideas, specifically focused on the manufacturers, on what their approach is to make hot water. And we're going to have another session in the engineering track next door at 4 o'clock on how to integrate that. It's then more a design question on how to integrate hot water making into multifamily design. So, close the door and be quiet, please. There we go. So I have some, it's a pleasure to have 3 of the panelists here. This is Mike, this is Alberto, and this is Justin. ClimateMaster, Enertech, and Ecoforest. Have you heard of Ecoforest? Yes. Very good. Hey, yes, hey.
I can save some slides then.
Yeah, so I had the pleasure to travel to Spain in February and look at their plant and see their technologies and enjoy the hospitality. So thank you very much, Alberto, again. But you know, we want to not focus on one manufacturer. We want to see what's going on in the industry, what's going on there. So this is what this panel is about 10 minutes, 12 minutes presentation, and then pretty much we want to have a lively discussion. I promised them I would ask tough questions, and you know, I consider making hot water kind of the holy grail of this industry because we need different temperatures, whether this is legit or not, but we're asked to provide them in higher ones. We're looking at different efficiencies. In my opinion, the hot water is utterly important to cool the geoloops in the summertime. Specifically when we're looking at you know, cooling dominated buildings, which just about every larger building is in New York State. So the important aspects of it. So this is why I'm looking forward for that too. Alberto, you're first.
Okay.
Are you ready?
I'm ready.
He's born ready. Good.
Okay, my name is Alberto Ferradas. Thank you for being here. First of all, sorry for my English. I will try to make me understand. Hope not to hit a lot the language. I work at Ecoforest. Ecoforest is a manufacturing company based in Spain. We began our venture in 2012, approximately. And our North American adventure began 8 years ago, more or less, with our partners in Canada, GeoSmart, and also with Phoenix. We work, they helped us to adapt the technology, the European technology, to North American standards. And okay, now we are going to talk about some technologies to improve the domestic water production. So I will go fast because I talk too much, and I think 15 minutes are not going to be enough if I am not going fast, no? So, okay, we began with our net zero product, net zero range, sorry, in 2018. So combining European technology with your technology here, with North American technology, okay? And now we have all our range of geothermal heat pumps, fully certified, Energy Star, AHRI, and so, okay? So, okay, a little numbers of our company. We are not a big company as our friends here. They are really powerful companies, but, okay, more than 200 employees. We are working in at the moment, more than 45 countries around the world. But okay, going to the important things, talking about the technologies to improve the domestic cold water production. Okay, some things, of course, the first one is to use the the heat pumps, the ground source heat pumps for producing the domestic hot water. They are the most efficient system for heating, cooling, and domestic cold water production, so much more efficient than traditional boilers, electrical heaters, etc. So it's a good point to produce everything with the heat pump itself, no? Another very important technology is the inverter technology, so the ability to adapt or to be able of varying the compressor power. That's really important in terms of efficiency and in terms of being able of reaching higher temperatures in the domestic hot water tanks, no? Because when you are heating the water, ability of the coils to transfer the energy to the water decreases because the delta T decreases. So if you can adapt, if you can reduce the power of the compressor, you can heat up for longer the domestic hot water, and you can increase this way 5 or 7 degrees the domestic hot water set point. No? So this is really important to be able to vary the power of the compressor with inverter technology. No? Another important point when you have a compressor that can vary, that can modulate in a complete range, is that you, most of the time, are working with oversized loops. That means that as you have more surface or surface for exchanging energy than the exact that you need, means that you have higher temperatures in the glycol, and that means that you are going to also have a better COP for producing domestic hot water. So this is another benefit of variable speed compressors. No? Okay, the use of electronic expansion valves, it's also important because this way you can decrease the overheating degree and you can increase the efficiency, you can decrease the discharge temperature, and this way also you can produce water at a higher temperature. No? So this is another important point, as the fact of using plate heat exchangers, because you are increasing the surface, the contact surface between the refrigerant and the water, and this way you can also increase the efficiency and the ability to produce water at a higher temperature. No? Okay, this is a very important technology that you are also using here. That means to install a desuperheater inside the unit, inside the heat pump, and also to install an additional circulation pump. It is what we call HTR technology, is high temperature recovery technology, and this is really, really important for domestic hot water purposes, no? For several reasons. The first one is that we can, this way, divide the circuits, and we have 2 circuits, one for heating or cooling, and another completely independent for domestic hot water production. So this means that, for example, in wintertime, we can produce domestic hot water and heating at the same time. Okay, so that is really interesting because we can increase the temperature of the domestic hot water tank up to 160 degrees Fahrenheit, more or less, okay? And besides, it's really important because we increase the efficiency of the domestic hot water production. For example, in that figure you can see there, we are producing water, the condensation temperature, you can see it's 105 degrees Fahrenheit, for example, for in-floor heating, no? So you are working with a COP up to 5, 4.5, 5.2, more or less, no? But the discharge temperature, even when the condensation temperature is 105 degrees, the discharge temperature is always higher. The discharge temperature in this case is more or less 140 degrees. You can see that we install an extra heat exchanger that faces the refrigerant when it leaves the compressor. So the compressor, when the refrigerant, when it enters into the superheater, it's at the maximum temperature. So we can take advantage of that temperature and produce domestic hot water also with the extra circulation pump that you can see there, the domestic hot water pump. And after that, we can produce heating, but with the efficiency corresponding to heating, because the efficiency is related with the condensation and evaporation temperatures or pressures. And we are working with the corresponding condensation temperature for heating. So this is really important because we can increase the domestic hot water temperature, and also we can do it with the efficiency corresponding to heating. We can duplicate the efficiency producing domestic hot water. So this is really important. Even more important during the summertime. Because in the summertime, sorry? Ah, okay, yeah, sorry. Okay, perfect. Because in the summertime, what we can produce with this technology is domestic hot water and cooling. Okay, this is even more interesting because the energy that we are taking from our homes, from our houses in the cooling process, instead of wasting it, instead of leaving that energy to the ground for heating the ground, or to the air, if we have an air source heat pump for heating the air, we are going to waste that energy. Because of the introduction of this extra heat exchanger, the superheater, that energy, we take advantage of it and we use it for domestic hot water production. This means that we are producing domestic hot water for free. Okay, so this is really important. In wintertime, it's important because I can produce heating and domestic hot water at the same time with a higher efficiency, but in summertime, I can say that I am producing domestic hot water completely for free. Okay, you can see here with a traditional technology, all the energy that we are taking from our house, plus the energy or the power that the compressor needs for producing that cooling, okay, we wasted it heating the ground or heating the air if it is an air source heat pump. So under these circumstances, we would be working with an efficiency of 4. If I am taking 4 kilowatts from the house and I am using, 4 kilowatts, 4 kilowatts is about 1 ton, more or less. Sorry for because they are European units, okay, but more or less just to make an idea, no? So the 4 kilowatts and the kilowatt that the compressor needs for the cooling production, we are wasting it. So we are working with an efficiency of up to 4, no? Just including this technology, these 4 kilowatts, plus the kilowatt that the compressor needs for the cooling production, we inject in the superheater, for producing domestic hot water. So now we have 2 useful powers instead of 1. We have this useful power, the cooling power, and we have the domestic hot water also as useful power. So automatically, we, instead of working with a COP or an efficiency of 4, we are working with an efficiency of 5, because both of them are useful powers. Okay, so it's a really, really powerful technology for domestic hot water, okay? In fact, this is not what we are talking about, but this can be even used for example, heating a pool also for free with the energy that we are taking from our houses in the cooling process, okay? So, a very interesting technology. So, more technologies. For example, EVI technology. This is more appropriate for air source heat pumps, so I will not talk a lot about this, but the air source heat pumps, they have a problem that is how to produce water at a high temperature when the temperature outside is low. Okay? Why? Because of the discharge temperature. If I'm working with a low evaporation pressure, the discharge temperature is too high and it can burn the oil inside the heat pump, and then we will have a big problem, no? So we don't allow, when we have very low temperatures outdoors, to produce water at a high temperature because we could burn the oil, no? If we introduce the EVI technology, it's like making a cooling during the compression process. So it's like doing the compression in 2 steps, point 1, point 2, then we cool down the refrigerant inside the compressor, we compress again, so at the end, the discharge temperature is lower than if we do just in 1 step. This would be the discharge temperature in 1 step. So we can work with the same condensation temperature, so with high temperatures for domestic hot water, even when the conditions are not so good, okay? We get this with, for example, the EVI technology. EVI means the enhanced vapor injection, okay? In fact, you can see here the 2 operation maps with 410A. This one, the blue one, would be without EVI, and the red one would be with EVI. As you can see, we have a big improvement when the conditions are not so good, okay? In this case, evaporation pressure or evaporation temperatures, okay? So this is another technology for increasing the efficiency and the temperatures you can get with, for domestic hot water, okay? Another very big improvement, of course, the new refrigerants. Here you can see a typical operation map with 410A. It's very similar with R32, very similar with 454B. The operation maps are really similar, okay? But see what the propane R290 can add to the equation, no? Instead of producing water at a maximum temperature of 140 degrees Fahrenheit, as we can get with 410A, okay, with HTR technology that I said before, we can increase the temperature 10 degrees or 15 degrees, okay? But with R290, besides it's a natural refrigerant, we can produce water at a temperature of 165 degrees Fahrenheit. I have to tell you that in Europe, for example, maybe this is good for you to know, in Europe, for the last 3-4 years, we have already regulations and normatives so that it is, we can work with propane. Not only air source heat pumps, monoblock heat pumps, but even ground source heat pumps. okay? So we have already there the regulations, and we can work with this refrigerant that besides is a natural refrigerant, and in terms of domestic hot water production, you can see the great advantage that it incorporates, no? So it's another good thing that in the future I am sure that here in North America also we will have regulations for this refrigerant, no? To finish, also to improve or to have better technologies for domestic hot water production, okay, the hybridizations. We can make hybridizations in all the parts of the heat pump, in the source, in the power supply, and in the load. In the source, for example, we can combine with a water-to-water heat pump, a ground source heat pump. Okay, it's in reality, actually it's a ground source, a water-to-water heat pump. We can combine borehole, okay, with dry cooler. Okay, so we have a hybrid source installation. The good thing is that the heat pump is going to send the glycol to the source or the combination of sources that it's more efficient at every moment. So why to talk about this when we are talking about domestic hot water production? Because, for example, in summertime, the air is more efficient than the ground, okay? Because the air is warmer than the ground, and we are going to increase the efficiency for domestic hot water production. Okay, this way of, or this kind of installations with hybrid source solutions, they have much more benefits, but at this moment, I don't see the paper yet, so I have more than 2 minutes, or? Okay, fantastic. But it is really good for domestic hot water purposes to make hybrid source installations, okay? Okay, in terms of efficiency, this is not so good, but okay, sometimes it is done. I mean, the heat pump can manage an external on an auxiliary system in case you want to produce water at a higher temperature than the heat pump can produce, okay, can produces. So, for example, you can install a boiler or an electrical heater or whatever. The purpose here is to heat the water the maximum the heat pump can, because the efficiency is better, and then to heat up maybe 5–10 degrees more with the auxiliary system, okay? So this can also be done because we can manage this auxiliary system from the heat pump itself, okay? And to finish, and the most important one in terms of hybridizations, this is really interesting as you are going to check, to make hybridizations between heat pumps and photovoltaic installations, okay? Naturally talking, it's a good marriage, okay, because I am combining two renewable energies, okay, heat pumps, they need electricity, and I am giving the electricity with another renewable energy, that it's the photovoltaic panels, and we can do really good things with this combination. For example, this is something really interesting. When I am producing, when I am generating surpluses with the photovoltaic installation, okay, the heat pump can, knows with the proper technology, the heat pump knows that we are producing surpluses with our photovoltaic installation, and it knows also the power that we are producing as surplus, okay? So the heat pump is going to consume, as they are inverter, they are going to adjust the power just to the surplus. That's important. So we don't exceed the surplus so that we have to consume from the grid. The heat pump is to adapt the compressor, the power of the compressor, the consumption, just to the surplus, and we transform that surplus into thermal energy. We are using our houses as a battery, okay? So we can increase, we have, for example, these base settings for domestic hot water, for heating, for cooling, for pool, for example. For example, in this case, 130 degrees Fahrenheit that I used as a set point, as I configured as a set point for domestic hot water, 95 degrees Fahrenheit for heating, 59 for cooling, and 79 for pool, for example. So we can configure another settings that we call the surplus settings, and basically we can say to the heat pump, go up to the maximum, to everything you can produce, to the maximum temperature. Okay, not for the pool, because you have to, not to, okay, comfortable temperature, okay? But in this case, when we have surpluses, as I told you before, the heat pump is going to adapt the consumption of the compressor to the surpluses, is going to consume the surpluses, and is going to automatically change the settings, okay? Instead of these settings that have been achieved already, because if not, we could not talk about surpluses, okay? The settings would not be, or the targets will not be these ones, but these ones. So we are heating up, we are producing domestic hot water, heating, cooling, or pool for free. We are transforming those surpluses, electrical surpluses, into thermal energy, okay? So we are going to consume less electricity from the grid. So this is another really interesting technology for domestic hot water production, okay?
Wrap up.
Sorry?
We have to wrap up.
It's on?
Yeah.
Okay, this is the last one, so. Sorry. Now, you can see here, for example, just in a schematic way, you have here the heat pump, you have here a separate domestic hot water tank, you have here a buffer tank, you can install a buffer tank or not. You can play with a thermostat and use your house as the battery, as the energy battery, increasing the temperature of your rooms, for example, when you have surpluses. But you have here the normal settings, and here the surplus settings, so that when we have a surplus, the heat pump knows, increases the power, consumes that surplus, and changes that surpluses into thermal energy to be stored in this equipment. So you can use your house and all your devices as energy batteries, okay? Okay, I think that's all. Thank you very much. Hope you understood everything I said. I talk too much, even in English, but thank you. Thank you very much.
So questions for later. Let's get through the talks first, and then we can talk a little bit about the technologies.
If you make any question, slow, because I talk very fast, but for hearing, it's not so easy.
So the very next one is Mike Hammond here from ClimateMaster. Looking forward for your talk and your technology.
All right, thank you. You ready? Yep.
Good afternoon, everybody. Again, Mike Hammond with ClimateMaster, and I'm going to talk to you about a unit that we have that produces hot water as well. Once I learn the button hit next, there we go. The unit we've had out for a little while now, it's we call it our QE model, our Trilogy model. It's a packaged geothermal heat pump that can also, it does dedicated hot water. So it's not a de-superheater. It actually does dedicated hot water, and I'm going to talk a little more about how that does that here in the next few slides. So to accompany the heat pump, we also have a specific hot water tank that has to communicate with the heat pump, and that's the tank you see next to it. And then we have, obviously, along with that, inside the unit, there's a pretty sophisticated control scheme, and with that, we have a communicating Wi-Fi thermostat that also, you know, you can remotely monitor, and you can see what your hot water production is. You can look at all these details. So I'll show you some snapshots of that here coming up. So here's kind of just the hub, you know, if you will, of the controls and everything that's communicating back to the system. And then our gateway out into the, you know, the online side of things is, again, through that communicating thermostat. And again, there's sides also for the contractor, where obviously we can see a whole lot more details. We can look at things like superheat subcooling. We can run the unit manually, remotely. So if it's necessary, you could be a little better prepared maybe for a service call or something like that from a technician standpoint. So this unit has 4 modes of operation. You know, like most other heat pumps, we do heating and cooling. But we can also do just straight on hot water only, domestic hot water, or we could do cooling and hot water at the same time. And very similar to what my colleague over here said, as far as whenever we're doing cooling and hot water at the same time, you're essentially getting one or the other for free, because we shut off rejecting any heat to the loop, and we're rejecting everything into the hot water tank. So depending on how you look at it, you're getting one or the other, you know, for free as a byproduct of the other. And you know, this gets with the program, you know, not being a de-superheater, it's full-on hot water. So, I mean, we're putting a lot of BTUs to it, and you'll see here in a couple other slides. You know, we have recovery rates that are as the same, if not better, than, you know, gas-fired water heaters. So, and again, that's why a lot of people like gas-fired water heaters, is because of the quick recovery rates. And again, with this kind of technology, you know, we can produce hot water at a much quicker rate. So here's just kind of a refrigerant diagram showing a little bit of the components. Inside the unit, we do have 2 reversing valves. One's basically acting as a diverting valve for hot water production. You see it right now, it's in the heating mode. We have electronic expansion valves. You know, this is an inverter compressor, one thing I did not mention in the beginning. This is an inverter technology, so we're fully variable with this between the, a certain capacity at the beginning and a capacity at the end, depending on the size of the particular heat pump. So for instance, it might go anywhere from 18,000 BTUs to 60,000. Regardless of the entering water temperature, it's going to make adjustments to give you those BTUs and the BTUs that we're going to need to put into the hot water tank. So again, when we're in the cooling mode, obviously we're just shifting a standard reversing valve just like you'd have in any other heat pump. And then cooling and hot water. Again, now you can see we've actually shut off the loop here on the this side right here. This is the loop braze plate. These are all braze plate heat exchangers in this particular model. And we've shut it off. We've actually closed down this EEV 100%, directing all the refrigerant over here to our EEV here that meters into this air coil. And that's then again where we're cooling the house. We're pulling the BTUs out of the house and then rejecting all those BTUs into the hot water tank. And then again, we could do just straight on hot water. So if there's not a demand for heating or cooling, we can do just hot water production. And again, we do not, but with our controls, we cannot do heating and hot water at the same time because this is full-on hot water. So again, you can't necessarily have two condensers. So in this case here, we would, with our controls, we look at priority depending upon where we're at, and we can shift, back and forth. And with being an inverter technology, we can go away from heating, and then we only let the temperature droop so much, and then we're going to go back to heating, and then possibly have to go back to hot water production. And if the demand is super great, we do have also backup electric elements. So again, a customer will not, run out of hot water, because not too many people would be too happy taking a cold shower, right? Here's just looking at a real-time run graph of a particular installation. And when it was making hot water is circled there. And it was approximately, and again, there was only hot water production. This blue area here, this is kind of mild time. You see, it was actually in May. So, and this is in Indiana when this was this particular home. So we were doing some cooling here, but in this point here was only hot water. And it took about 34 minutes to make that hot water. And if you run some calculations, a standard electric element is 4,500 watts. And if you look at the BTUs, of a 4,500 watt element, you're looking at about 15,354 BTUs. Well, to take an 85-gallon tank from 100 degrees to 125, you do the math, and it's about 1 hour and 9 minutes. Well, to do the same thing, again, with this particular unit, when it runs in the hot water mode, the BTUs that we're putting into there are basically double that, and it's about 36 minutes. So, hence, right on par with what we're seeing right there, on a real job site. And again, when you look at a gas-fired water heater, typical gas-tanked water heater, you're looking at the input here on a typical, say, 50-gallon gas-fired water heater. Well, you may be putting in 40,000, but you're not getting all 40,000 into the tank, right? There's obviously combustion, and we've got a flue. And so when you look at this is, right off a particular manufacturer's specifications, they're putting in 28,000. So again, with this unit, we're over exceeding that. And again, thereby, quick recovery rate. Here's an actual case study from Oak Ridge Labs. With this unit, we've done a lot of partnerships with those folks over the years, and this is a particular one of the case studies here in Oak Ridge Labs here in Tennessee. And this is a simulated house, a house that is actually built, but they do simulated living in the house. There's actually not people living in there, but they're running other appliances, dishwashers and other things, just as if it was a family living in that house. And if you look at this particular one, it's about 3,700 square feet. Again, a high-performance envelope, non-occupied again, but they're simulating these internal loads just as if there was a family living there. And so this particular study, they modeled it on various cities throughout the United States and then showed the operating cost and savings here over these three different types of systems. A baseline system was an air source heat pump, 13 SEER, and then the middle option was a 2-stage heat pump utilizing a hot water generator, pretty typical out there in the industry. And then this variable capacity option here, the model I just showed you, where we're producing, if not all, most of the hot water directly from, the heat pump. And here's some of the results. So if we're looking at, this is, see here we got Atlanta, we got Phoenix, and we got Chicago here on this particular chart. And then you could look at the kilowatt consumption based off that model home and those various locations, and then the potential savings. So let's just, since we're primarily here talking about this variable technology, let's look here at the variable speed heat pump, and especially the hot water here. We're looking at like 74% savings, over that traditional. And again, significant savings here, as you see even in other parts of the country in this model. And I can tell you, living with one of these myself, I've had one in my home for many years. It's tremendously comforting system as far as operation, but also tremendous hot water savings over just even a hot water generator. Again, just in summary here, and then I'll close and turn it over to the next speaker, is, again, we showed overall site energy reductions, 25 to 30%. But with the integrated hot water, we're 50 to 60%. So again, with this kind of technology, there is significant savings. There's a lot, and depending on the home, there's a lot of potential energy savings in the domestic hot water side as well. So I want to thank you very much, and I'll turn it over here to the next speaker.
Okay, sounds good.
Very good. Justin from Enertech?
Yep, Enertech. How's it going? We're gonna make this pretty quick, I guess, so I might just use an arrow keys here. So I'm with Enertech. Most of you have probably heard of us. If you haven't, stop by our booth over in the other room there. But we'll get into this real quickly. We have a couple of different options for heat pump technology doing domestic hot water. Like the two gentlemen that went before me, both of ours are inverter driven. We have a ground source option as well as an air source option. We have an air to water heat pump, so it's a little bit different than just your standard air source. We do things a little differently than the two guys before me explained. We approach domestic hot water with just larger capacities. So we have the ability to shove about 60,000 BTUs into primarily or directly into domestic hot water with just the heat pump, with either one of the two that you see on the screen here. And we do things like direct to load piping strategies, which I'll get into here a little bit. But benefits of these type of technologies, we have a water-based system, so we're doing all hydronics instead of combining forced air along with domestic hot water capability. We are a hydronics-based system. And because of this, it makes it extremely flexible. You can do a lot with it, but moving BTUs through water lines is just a lot more efficient than doing it with air. We can carry as much energy through a 1-inch diameter water pipe that we can through a 10 by 14 duct. So we just feel that this is a smarter way to go and making things more efficient moving forward. As spaces and homes become a lot more expensive to build, and building materials and labor and everything else goes up, having dead space to run ductwork in is just becoming more of a commodity. So moving forward, you can do a lot with PEX tubing. It's getting cheaper all the time. We have the added bonus of doing up to 100% of domestic hot water. We can replace things like boiler systems. We can do things like baseboard heaters and radiators, as well as do forced air. We do heating, cooling, domestic hot water, and like I said, we no more buffer tanks. So we go direct to load and kind of have a truly variable output system. Some of the benefits of doing variable speed hydronics, we can really, anything that you can heat or cool with basically 40 to 140 degree water, we can do with these units. So things like radiant floor heat. We can work off outdoor reset. We can do standard ducted hydronic air handlers. We can do decorative or any manner thereof panel radiators, baseboard heaters. There's literally countless options when it comes to fan coils, individual fan coils. This one here is kind of like a traditional mini split look for a high wall, but you actually pipe water to that. And then of course doing domestic hot water. Like I said before, we approach the domestic hot water a little differently. And so we actually use a reverse indirect tank, which I have a little bit larger view of here. So our heat pump sitting off to the side, we're actually putting 100% of this heat pump's energy into this tank, so we can have incredibly fast recovery times. We also have options for dual fuel or electric backup, where we're actually heating the water with a backup heating element or some type of backup boiler. But this gives us some good standing storage here, as well as a tremendous amount of surface area on a heat exchanger, and we're able to produce a lot of domestic hot water. And real quickly, I guess we can go through a few what this actually looks like in practice. So this project here is a pretty simple, basic project. We have a couple of radiant zones. This here is a variable speed water-to-water heat pump. What this homeowner decided to do was put in a gas furnace for backup, and we have a hydronic coil sitting on top of that gas furnace providing forced air heating and cooling. And we also have one zone that has a small air handler or small fan coil that's up in the garage, so we can do heating and cooling in the garage space as well as heating and cooling for the house and not share air between the two spaces. And then here's the domestic hot water heater right here. So with this one box, doing forced air heating and cooling for the home, two zones of radiant, plus heating and cooling the garage, and 100% of the domestic hot water. It's a pretty simple setup. And like I said before, no buffer tanks, direct to load piping, internal load pump is built into this box. So this is just one of the systems that we offer. This one here's close to where we are right now in Poston Kill, New York. This is the air-to-water heat pump. And this house, I don't have a picture of the air handler here, but this is the indoor module. We're doing the domestic hot water here again. We did put in a radiant manifold for future expansion. And there's an air handler. So this system replaced just a gas furnace with a standard air conditioner. So there really was no hydronic component to this home. But they wanted the benefit of doing all the domestic hot water with the heat pump and then future expansion capabilities to add panel radiators in the future, which they still have not done. I actually talked to this homeowner's father the other day, and they still haven't hooked anything up to that, but it's there in case they want it. But these systems can get a lot more complex. They can be multiple units like this one here. This one here is, again, direct to load piping, no buffer tanks. We have 3 heat cool air handlers being run on this unit on the left and 3 corresponding radiant zones. We have 1 heat cool air handler on the right unit with 2 radiant zones, also doing the garage and the domestic hot water for this house. Because we do things with direct to load piping and no extra tanks, we just have the 1 tank, or it could be multiples depending on what the size of the house is and what the domestic hot water requirements are. This is a pretty good representation of a little bit larger home, but still has, I think there were 4 or 5 people living in this home. So we're able to do that 100% of that domestic hot water load with just 1 80-gallon tank. This is the flow center here in the middle. Variable speed flow center, flow in the ground loop with 2 5-ton variable speed water-to-water units. So pretty straightforward. All the zone controls and everything is on that wall. And for those of you that have seen systems like this before, this one's pretty simple for how much is going on in that home. This one's out in Washington State, in Anacortes, Washington, if anyone knows where that is. It's a beautiful area, but this was a boiler replacement. This was a project that was existing, took a boiler off the wall, switched it over to heat pump technology. So we've got the air to water heat pump sitting outside, as well as the indoor module. We're doing 100% of the domestic hot water. We also added cooling capabilities to this house. So originally the home was built without any cooling. It was just baseboard and radiant floor heat. So, you know, switching over to heat pump technology, when you can heat and cool that water, it opens up the doors for a lot of possibilities. And then this one, you can see that I didn't make all these pictures pretty. I wasn't expecting to show these off to everybody, but I should have removed the cardboard here. But this one's fairly complex. This house is actually in Connecticut. I just took this picture like 2 weeks ago. And 2 variable speed water-to-water units. This one has 2 domestic water heaters just because they had incredibly large domestic hot water usage. And there's a lot of zones. This one's pretty complex. There's a lot going on, but no buffer tanks, everything's direct to load. It's a pretty involved project for sure. And then this one here is another air-to-water system, just showing the integration of a backup boiler. This particular boiler is a gas-fired boiler, but it could be, you know, a pellet boiler or whatever, any type of backup heat source. But it's a pretty good representation of direct-to-load piping as well as doing domestic hot water. So I got the water heater over here on the side. We've got all the zone valves. These are heat-cool zones as well as radiant zones. So it just shows a lot of the flexibility that that you have going to a hydronics-based system. I know a lot of people are kind of concerned about making that jump into hydronics, but it really opens up a whole new bag of tricks, and you can really do a lot with it. So with that being said, all right, that works? Right on. We'll blow through it fast. Thank you.
See, it becomes more and more important to look at hot water because it's really not worth keeping the gas distribution network online for a much smaller amount of energy. If we decarbonize the heating, what about the domestic hot water? Keep in mind, domestic hot water on average is about 17–18% of all the building energy usage. So, and that's in private homes. We're talking about 40–50% in multifamily homes. So this is an important subject. Any questions so far from the audience? Any grilling? Yes? Yeah, we got
Hi.
rules here.
I'm Kristen McMurray at RMF Engineering. My question is for Justin. Yes. When you're putting in these hot water installations, or chilled water too, you're having to rip up the house pretty significantly to make the changeover from the vents to the piping, or is it not so bad?
Well, I wouldn't.
Oh, you gotta turn it on. Yeah.
I wouldn't convert a home that was originally built with forced air over to hydronics. That would just be pulling out the gas furnace and putting a hydronic air handler in its place. There are many products on the market that allow you to like put radiant floor over top of an existing floor, whether it be concrete or wood. You're not really tearing a lot up, but they are costly. So most of the time, you know, a house is either built as a hydronics-based home or a forced air home. It's a little bit difficult to retrofit after the fact. But like I said, we can pull out a gas furnace and an air conditioner, put a hydronic air handler in place of the gas furnace, set this heat pump next to it, and then have, you know, 100% capability on the hot water as well as heating and cooling. So, but the delivery system stays the same in the home.
Okay, thank you.
Yep.
Any other questions? Yes.
Hi, Martha Sickles, Urbicon LLC. I'm just wondering if any of you have ever converted a steam system over to a hydronic or air system.
We're talking for hot water, or
I guess that's a no.
Or are we talking to
For heating, or?
Are we talking hot water only, or are we talking hot water for heat? Both.
It doesn't come up that often here in the States, mainly just because most of the steam, or well, all the units that we all discussed here today are really residential based, and it's just not that common to see a true steam system in a residential setting. Not to say they don't exist, it's just not super common. But yeah, I have not done a true steam system and converted to heat pump.
It's being done right now. We're doing that here in the city, in New York City, not here in the city in Albany, in New York City. But we are, and we're going to talk about this in 2 hours when we're talking about multifamilies. It's not really that common in residential, he's correct, but it's used here in older buildings for domestic hot water as well as heating at the same time. We recognize that. Let me ask you a question here.
Yep.
Just for me to clarify, which one of your technologies has an on-demand heating where you can turn it on and turn it off when it's needed, so it can use 100% of it? Because we all use the term de-superheater. A lot of these superheater technologies only work when the heat pump is actually running, specifically in the summertime. What are we doing in the shoulder season? We realize it's not that important because the shoulder season is not where the electrical grid is going to be at peak. But I just want to clarify what your technology is, number one, yes, and number two, where do you see this going?
Great question, and yes, the product I discussed up there is a dedicated hot water, so it's not a de-superheater that only reacts when you're heating and cooling the home. It will react only to a hot water need if there is no need for heating or cooling, such as milder weather like we're experiencing now in most homes. You may not be heating or cooling, but we can still provide all the hot water with the geothermal heat pump. So I see more and more technology as it goes forward. We're probably going to look at more things like that from our end. You have something? Sure.
Thank you. Okay, yeah, in our case, I didn't say that, but in our case, we have the superheater inside the heat pump, but you can produce 100% of the domestic hot water. I mean, we have 2 heat exchangers, one when the refrigerant leaves the compressor, the superheater, and we have then the main heat exchanger, that it's the condenser when we are producing heating or the evaporator when we are producing cooling, okay? So in our case, we take advantage, we can make recovery or not making recovery. I mean, we adapt to the needs you have. In our case, in fact, you have to configure 2 different temperatures for domestic hot water, okay? 2 different temperatures. The normal setting, I don't know, for example, 140, 130, the minimum temperature you configure, the maximum efficiency you are going to get from the technology. So for example, 130, that is the normal setting for domestic hot water, but then you have to configure another setting, that it is the HTR setting. And that setting, you go to the maximum, I mean, to 160 degrees. So when you have a big demand for domestic hot water, for example, you have 2 showers in a very super short period of time, and the temperature inside the domestic hot water tank decreases the minimum you have configured, the normal setting, then the heat pump is not going to produce simultaneously heating and domestic hot water or cooling and domestic hot water. The heat pump is going to produce only domestic hot water, and besides, because of internal design of the heat pump, is not going to use the superheater for producing domestic hot water because it's smaller and it would need more time, and the circulation pump is also smaller. It will use the main heat exchanger, the condenser if we are in wintertime, on the evaporator, or the evaporator if we are in summertime. So we are going to produce the domestic hot water very fast, 100% of the power of the heat pump, for reaching that minimum temperature that is comfortable for you. Okay? Once that temperature is achieved, then it's when the heat pump is going to produce simultaneously heating and domestic hot water and cooling and domestic hot water, because you are satisfying your main demand, heating or cooling, and you are heating up. It's going to need more, it will need more time because the superheater is smaller, but it's the end because you have the minimal setting achieved, okay? Because you have used 100% of the heat pump for achieving that minimum setting, okay? For example...
So you tell them to prioritize on the hot water?
Yes,
You have that
exactly.
setting,
Depending on the temperatures that you configure. What happens in summertime, for example, that when you are usually take a shower at a lower temperature of the water, most of the time when you have a consumption or a demand for domestic hot water, the temperature of the tank is between those temperatures, the 2 temperatures that you configure. So you are using recovery or the superheating always. But if it is necessary, all the power of the heat pump is going to go for producing domestic hot water very fast with the main heat exchanger.
Yeah, Justin?
Ours are on demand as well. Come on just to do domestic hot
Just
water.
use a mic. Yeah.
So yeah, both of the heat pumps that I showed, they are not a de-superheater circuit. They run 100% of the heat pump's energy if needed to the domestic hot water heater.
Very good.
Yep.
Okay, we're a little late. Only a little, amazingly little. Normally we are way overshoot. And so yeah, thank you very much for attending. Grab our speakers down there, outside. Thank you very much. We talk more about domestic hot water in an hour or so, hour and a half. For multi-families. Hey, all good? Yeah, it's all good.